Conference will now be recorded.
So good morning or good afternoon, everyone. My name is Dorothea Iovino for CMCC, settled in Bologna, Italy. I'm co-chair of the Climate Ocean Modeling and Development Panel, which is hosting this webinar series. Today is our third webinar. It's my pleasure to introduce our speaker, Anass El Aouni. Anass is an oceanographer at Mercator Ocean International, where he works on a machine learning-driven ocean forecasting system. Before joining Mercator Ocean, he completed a PhD in applied mathematics, focusing on ocean dynamics and Lagrangian current structure in coastal dwelling region. And then he moved on to ocean modeling and machine learning in his postdoctoral research position. So thank you, Anass, for joining us today. Before
Thanks
we
for having me.
just a quick note on logistics. So please keep your microphone muted during the talk. Feel free to type your question into the chat. You can also ask them at the end just by raising your hand and speaking directly. Manita Choksi, that is co-chairing the panel with me, will moderate the Q&A session. Please also note that the talk will be recorded and then will be available through the Clever YouTube channel. So again, to be quick, thank you all for joining, and thanks again to Anass. So I'm happy to hand over to you. And Anass is going to present GLONET. This is the Global Ocean Neural Network-based forecast system, probably already news anyway, developed at the Mercator Ocean International. Thank you, Anass.
Thank you. So hello, everybody. Anass, I'm with the Mercator Ocean International, and today I'll be talking to you about GLONET, which is Mercator's first end-to-end neural global ocean forecasting system. The way it was designed, the way it was trained, evaluated, and how it is operating. Also, the ways it was actually evaluated and how that was actually packaged into new projects for the ocean forecasting community. And finally, some ongoing projects following ocean GLONET model. So let's actually start with the basics. What is forecast? Actually can be seen as the following. Even the present state of the ocean, we would like actually to predict its future. And this is generally done based on our understanding of the ocean or the system in general. And of course, during the last few decades or so, our understanding of the ocean allowed us to build these large circulation models that are based on the primitive equations. These models actually tend to be highly interpretable and trustworthy because they are rooted in the physics we pretty much all understand. But on the other hand, they tend to be computationally very expensive and memory intensive because they require huge HPC capacities. We're talking about thousands of CPU units along with the memory that comes with it. And they're also quite difficult to improve given more data because they require a lot of data assimilation scheme, parameterization, you name it. And now actually let's kind of rethink this problem and let's say that our understanding of the ocean might be limited, which is pretty much true. And now we would like actually to predict the future state of the ocean, not based on the physics we understand, but rather based on very complex patterns that are embedded in the data itself that we observe. And this is pretty much the idea behind most of machine learning models. So machine learning models tend to be highly competitive in terms of accuracy. And we have seen this in the atmospheric machine learning community. They tend to deliver extremely fast predictions compared to the numerical models. And their performance actually do improve given more data. But on the other hand, they kind of like the versatility of numerical model. So you would not expect to train a model for short-term forecast and have it running for climate projection or even for seasonal forecast. But this might not last so long, especially if you look at the speed of which a machine learning atmospheric community is moving with, starting with very, very basic architectures in early 2020, up to very complex and very advanced architectures in nowadays. We're talking about a lot of advanced models, some of them or most of them actually have operational capacities, and some of them they're already entering operational pipelines. And of course, where is the ocean and all of that? Well, a little bit behind, but we're starting actually to catch up with most of works actually taking place in 2024. We're talking about models that are actually capable of outputting three-dimensional ocean state at a very high resolution of that of 1/12 degrees. And some of them, they are having operational pipelines, and some of them, they're already entering some. So given all of that, in Mercator, along with our physical models that are delivering operational products on a daily basis through the Marine Copernicus service, we're also kind of faced with the need of exploring opportunities within the world of machine learning, particularly to open new opportunities such as speeding up the forecast process, allowing new services such as on-demand forecast or reforecast, also to allow users to run forecasts with their own initial conditions, also to address research questions that require studying a lot of what-if scenarios. That means running a lot of simulations at a very low cost. And also this world of machine learning would help us to deal with the ensembles and the storage capacities actually that comes with it. And given this context in Mercator, back then we decided to develop GLONET through our digital twin of the ocean, EDITO, as our first system. So GLONET is actually architectured to capture multi-scale dynamic of the ocean through a series of interconnected components. It starts by processing 2 consecutive days through a temporal block, which actually extracts meaningful feature maps that do encapsulate both the initial conditions along with the forcing. And this here would be basically a fully convolutional neural network. You'll have to design in a way that the number of input channels are going to be increased by 2 as output. So you'll allow for the forcing. Then these informations are going to be processed by a spatial block, which basically has 2 components. The first one operating at the frequency domain, and it's actually designed to capture large-scale circulations. That means teleconnections and everything that is large circulation. And it is basically a Fourier operator built on the backbone of a transformer, also formerly known by adaptive Fourier operators. And the second module here consists actually of a fully connected convolutional neural network with the smaller kernels. It is all designed actually to capture small-scale localized features and interactions. And then these informations are going to be processed by an autoencoder block, which is actually designed to fuse these multi-scale circulations into a unified latent representation before projecting it back to the physical space to reconstruct the forecast. So as for training, GLONET now is actually operating at 1/4 of the degree, and it is actually characterized by 21 vertical levels from the surface down to the seafloor. And it is actually trained on our reanalysis product, GLORIS 12, between 1993 to 2020. The year of 2021 actually served for validation, and as for testing, we used GLO12, which are our operational product for forecasts and analysis. So GLONET is actually designed as the following. It takes the initial state of the ocean, that would be the ocean current, the salinity, the head sensation, the temperature, and it is going to output the same variables through an autoregressive fashions. As for training, GLONET is not a huge model. It has only around 250 million trainable parameters, but it's pretty much hard to fit it into a single GPU. This is why during the training, we use something known by model parallelism, where you'll have to spread different parts of the model across different GPUs within a single node. And of course, we used a total of 8 nodes where we used data parallelism to speed up the training and also for better generalizations. So between training and fine-tuning, I would say it took around 2 weeks in total. So after 2 weeks, your model is ready for evaluation and, of course, to enter operations if necessary. So following the operational protocols, once it is trained, GLONET actually could deliver 10 days forecast in less than 7 minutes using a CPU unit. And this goes down around 30 seconds using a smaller GPU unit, and only 3 seconds if you're using large GPU unit. That would be for 800 GPUs, which could be translated to, let's say, 1 year of forecasts in less than 3 minutes in total, which is pretty fast compared to the numerical models. And to assess the performance of GLONET, we actually did benchmark it against 2 models. The first one would be GLO12, which is our physical model that is delivering operational products on a daily basis through the Marine Copernicus service, but also against CHIHE, which is to be seen as the first data-driven ocean forecasting system developed in the community in early 2024. And these evaluations actually do include a class 4 matrix, generally used to intercompare physical models under a unified framework, in which actually we compare all the physical models to the observations. Also an OECC framework, in which actually machine learning models are going to be compared to the data they used during the training. Here we're talking about GLORIS 12, but of course we are going to isolate a period of time that was not used during the training. That would be 2024. And of course, beyond these point-weight evaluations, we are also proposing a series of process-oriented metrics that are designed actually to assess the physical plausibility of their forecasted variables. But before going ahead with this evaluation, I would like just to touch up quickly on CHIHE, as it's going to be carried through the whole evaluation and next slides. So CHIHE, as I said before, is one of the first machine learning models developed in the community in 2024. And it is basically architectured following transformers architectures, one of the architectures behind most of the large language models. And it works as the following. So at the initial stage, the input data are going to be patchified into small patches. Then they are going to be plotted into a certain embedding dimension, then sent to the ocean blocks. And each of these ocean blocks actually, they have 2 components, a simple transformer, which is designed to capture local dependencies, meaning everything that is mesoscale up to regional circulation. And also a swing transformer, which actually utilize group propagation along with the multi-head cross attention to capture global patterns, which mean teleconnections and large circulations. And of course, you'll have 5 of these blocks operating at different scales before sending at the end these embedding tokens into an MLP head for patch restoration, and therefore you will have your forecast. And as for training, they used more or less the same data. I'm talking about GLORIS here. They used GLORIS between 1992 to 2017, kept at its original resolution, which is 1/12 degrees. And they actually forced the model with ERA5 product, particularly the wind 10 meters above the sea. And also they made use of OSTIA for boundary conditions. And as for design, CHIHE is not an autoregressive model as GLONET or other numerical models, but rather it is a direct forecast system, which actually trains separate instances of models, each designed for a certain lead day. So it's quite different from the other. Now, back to the evaluations. So as I said, the first set of evaluation actually here consists of comparing the model's output directly to the observations. And this is generally done on a point-wise basis. So to my left, you can see the evolution of an RMSE as a function of time. And generally, we see that all models are quite competitive, each leading in a different certain lead day and certain variables, pretty much what you would be expecting. And to my right side, you would have the spatial comparison of the machine learning models compared to GLO12. Positive values here are denoted in red, and they are going to tell you that there is an improvement relative to GLO12. Meanwhile, the blue values indicate actually degradation. Again, more is the same conclusions. Each model tend to be better in a certain region, following certain regimes, certain variables, and of course, certain lead day. Now moving to the second set of evaluations we did propose. Here we propose to compare all the models, only the AI models or machine learning models, to the data they used during the training. That being said, it's glorious 12, but of course, a period that it hasn't been used during the training. So the first figure here is showing how models are actually performing across various depths, while the second one showing how they are actually performing across different lead time, of course, at the very first level, which could be the surface. And again, the results are quite competitive, each again leading in a certain variable and a certain lead day and level. So the question we should ask ourselves right now is, this type of evaluation is enough actually to kind of trust these machine learning models, especially knowing that most of machine learning models actually are trained to optimize the loss functions, which generally tend to be pointwise and more likely to be in RMSE, which is actually the case for GLONET and also for CHIA. And the answer should be actually no, and this is why we did propose a new set of evaluation. Let's call it process-oriented evaluation, which is a series of metrics that actually try to check the physical consistency of their forecasted variables. So this type of evaluation tend actually to check the capacities of these models to derive physical quantities that were not actually used during the training. For example, we could derive the geostrophic component of the current from their forecasted SSH. And as you can see, GLONET here shows clean and identical patterns to those that of physical models. Here it's glorious 12. Meanwhile, CHIA's output are pretty much noisy, revealing a lot of artifacts which actually were embedded in the forecasted SSH and actually cannot be seen by the naked eyes. Just actually to clarify, I know it doesn't make any sense to plot the geostrophic current around the equator, but it is just to highlight the type of noise we could see and how they're actually distributed across the globe. Another thing we could do would be to try to reconstruct the mixed layer depth. And this actually would give us this time information about the coherency across forecasted variables, particularly the temperature and the salinity. And again, GLONET shows closer patterns to those of glorious 12, less noisier, revealing actually consistency across forecasted variables, which is actually not the case of CHIA, which is revealing either inconsistency across forecasted variable or just simply quite a lot of artifact that makes it pretty challenging to reproduce a plausible mixed layer depth. Another metric we did actually also check while preparing GLONET was check the capacities of AI models in preserving dynamic consistency, energy cascading, and especially fine-scale structures. And the example I show here is pretty simple. Tells you exactly the capacities of the models in preserving small-scale dynamics and high frequencies over time. And this is pretty simple to do. You just have to move to the frequency domain, define your modes, and then define your noise cutoff, and check how the energy evolve actually across different lead days, which actually revealed here that GLONET is pretty much consistent up to 10 days. It's very comparable to the physical model, GLONET here. But this is not the case of CHIA. And you can see the initial conditions. We have a lot of high frequencies that are all smoothed out by the 10 days. And this could mainly be due to the way it was designed. So as I said before, it is direct system, which has a lot of models each trained for different lead days. And it's pretty much challenging to keep the high frequencies and try to forecast the 10 days based on the first day. And this is one of the reasons why we see what we see here in these images. Also, what we did check here is another evaluation, which could tell us a lot about the dynamic consistency, and that would be through Lagrangian analysis of drifters. So the setup is pretty simple. We just have to initialize a uniform distribution of particles across all the red boxes you can see here around the globe, and advect these particles for like a period of 10 days for the whole period of course, of 2024. And see how these trajectories are going to diverge from those of glorious 12, which is here the reference. Results shows actually that GLONET has a little bit of the edge, but not by much. compared to Chihe, which is quite surprising, knowing that Chihe is not an autoregressive model, but has a lot of separate models, but still actually managed to reconstruct fairly plausible trajectories. And this could be attributed to the interpolation, both in space and time, while computing actually the Lagrangian trajectories. This could be one of the reasons. And one last exercise would be here to simply apply an AD detection algorithm to the HSS output, and in which, for example, you could define an AD as the outermost convex contour of the SSH. We could apply this algorithm for different lead time and see how these structures actually going to be evolving in time. And again, this exercise revealed that there is a consistency in GLONET compared to Chihe, where a lot of smoothing and pre-processing is required for the SSH before applying this algorithm. As you can see here, the initial EDs, for Chihe, they appear at the initial condition, but they kind of vanish all with lead times. And this is mainly because of the noise or artifact that do actually break the convexity of the initial EDs. So just a word or two about what we have seen so far. So the ocean community is actually entering the era of machine learning, and we'll be expecting more and more models to be developed. And if anything, we really should work on the way we validate and evaluate these models. And more importantly, we should have a unified framework to standardize the evaluation and validation, both for actually physics and machine learning models. And in fact, let me go back to one of my previous slides. What I said before is we have witnessed quite a lot of advance and development in the machine learning atmospheric community, but I didn't really tell the full story. One of the reasons behind this success is having actually a community-driven benchmarking framework, which allows users to intercompare their model and their unified setup. And this actually was the case of WeatherBench. So WeatherBench is a framework, basically a Python code that implements a lot of evaluation metrics developed in their community. And also it is a common dataset that allows any users to evaluate their model and know how they are going to be ranked among other models in the community. And now back to the ocean. As I said before, again, we're starting to gain momentum, and now the ocean community is starting to use more of machine learning to develop ocean emulators. And in fact, the current state of the machine learning ocean modeling now looks somehow like this. We have more and more coming models, both at the global scale and at the regional scale. So it's pretty much the right time for us, for the ocean forecasting community, to have their own benchmarking framework. And that is the case here. It's called Ocean Bench. So as any benchmark in the machine learning community, it comes with a scientific paper that describes and demotivates the metrics, but also an open source framework that can be used by anyone. So Ocean Bench could actually be seen as the following. It is a reference dataset against which actually machine learning models, either physical or machine learning, could be actually compared to. Few candidates. In the current version, we have 4 in total. And of course, evaluation metrics that are packaged into a Python, well-written and easily accessible by anyone. And basically here, most of the evaluation we have done for GLONET, we just package it into this new project. And finally, a process and the resources that actually could orchestrate everything, starting from getting access to the data, evaluating, and finally reporting the scores into a headline website. So the project, as I said, it is as following. In addition to that, it has a documentation website and many other things that you could actually check in the project or the GitHub project. And the current headline table of Ocean Bench would look somehow like this. As you can see, we have 3 main tracks. One, when you compare the models to the reanalysis, basically the data they use during the training, or you compare them directly to the observations, or you compare them to the analysis. And what is actually very interesting here is the way the models would behave compared to the way you actually compare them to So if you compare them, for example, to observations, machine learning models tend to do slightly better than the physical one. Here we're talking about GLONET, which serves as the baseline. This quality would degrade a little bit for certain variables if you compare them directly to reanalysis, which is the data they use the training. And of course, this goes all red if you compare them to the analysis, which are basically made directly from the same model, which is GLONET forecast. And of course, as any benchmark in the community, it should be updated regularly. So for the future release, which we hope to be done before May, we would like to extend the evaluation period to include 2023 and 2025. Also, we're planning to include more of models as challengers, both in physics and machine learning. We have FESM as physical model. We have GLONET, which is an ensemble-based model. It is pre-operational at Mercator. We also have high resolution, such as GLONET 36, which is also another high resolution model, also pre-operational at Mercator. But also some of the machine learning models. We have Langaya and Fuji Oceans that were published in 2025. And of course, some of the regional models, such as CCAS and Midformer. As for the evaluations, of course, we are going to include everything that is probabilistic, in which the GLONET is going to serve as the baseline. Also, some regional models as highlighted in red. And of course, we also are going to include the 1 degree track to allow users or groups with smaller computational capacities. And of course, we are going to extend the forecast to include also seasonal and also extend to other aspects of the ocean, including the sea ice and the biogeochemistry. And of course, we would like also to include more of the evaluation metrics, such as the power spectrum density, more of process such as AD detection and tracking, both in the Lagrangian and Eulerian frames, and some other probabilistic metrics such as CRPS. Now back to the ocean forecast and GLONET. So as I said before, GLONET was actually developed in late 2024. And as for now, it is being or living in an operational pipeline, different from that of a typical numerical model, which requires a lot of or huge HPC capacities. GLONET now actually is living in the cloud, and particularly that of EDITO, the European Digital Twin of the Ocean, and works as the following. So it requires a small CPU unit that is triggered every 10 minutes. And it is designed to check whether the initial conditions are available or not through the Marine Copernicus service. If that is the case, it is going to trigger another or book a GPU, a smaller one, in which is going to be or going to upload the weights of the model along the libraries to run it, run the forecast, start the cataloging, and therefore after that users could access to the data through either the EDITO viewer or access to it directly to EDITO using Jupyter notebooks, so they could play with the data the way they want, or they could also access to it through Ocean Pro software, which is quite an advanced tool that allows you to visualize data and do a lot of analysis. And now moving beyond the GLONET, I did actually prepare the 2-3 slides to talk about ongoing works under the same context, which is ocean forecast. So moving beyond deterministic forecast, we are currently developing a new machine learning model, not only capable for accounting for uncertainties, but also capable of achieving a longer rollout from seasonal forecast up to climate projection, we hope. And our new integrated ocean emulator that we are currently developing is based on 3-dimensional multi-scale graphs, where only nodes actually representing the ocean are kept. And it is designed to follow a classical autoencoder architecture, allowing it to learn a latent representation of the ocean, where the fusion process actually is applied to account for uncertainties. Basically allows you to sample different forecast realizations from the same initial conditions. And the system we are developing is designed to output all sides of the ocean, we hope, including the physics the biogeochemistry, and the CIs. And it's actually trained on GLORIS. Particularly, we're talking about the ocean currents, the temperature, salinity, and SSH, the sea ice velocity, thickness, and fraction. And it's also trained on BioMer, which is a hindcat simulation using PSCAS model between 1993 and 2020. And it has the following variables: the chlorophyll, the nitrate, phosphate, primary production, dissolved oxygen, and silicate. And contrary to GLONET, now we are forcing our model using ERA5 product. We're using the wind above the sea, the temperature, 2 meters temperature, and similar information about the pressure. And so the current configuration of this emulator we're developing is operating at 1 degree of resolution, and it has around 8 vertical levels covering the upper ocean, and it has a monthly time step for now. And it is trained using 4 H-under GPUs in total for a period of 1 week in total. So it's pretty much a small model. It is 1 degree, but still it occupies a large GPUs. And there is a reason behind that. But once it is actually trained, this emulator is capable of delivering over 100 years of projection in less than 15 minutes for a single resolution. And we could imagine with multiple GPU system, we could easily deliver 15 members in less than an hour. Of course, once it is trained to optimize CRPS or other metrics to have nice spread. And actually, this shows the potential of these emulators in addressing key issues such as what-if scenarios, seasonal forecasts, and hopefully also could be useful for climate projection. And as I said before, this is an ongoing project. And future step for us would be to upscale to full ocean column. Also perform a proper evaluation of the system. We're also aware of a lot of machine learning models in the community that are pretty much stable up to climate scale. And it also would be nice to see the capacity or the ability of us coupling them with these ocean models. And for future plans, successful implementation of this would consider integrating it in EDITO to allow new services, and particularly services that allow users to interact directly with the data on the model itself, and also that allows users to run some scenarios such as what if, where you could use your own initial conditions. For example, you could consider MCDR scenario or carbon removal with different scenarios and see what your setup would give you. And in order to achieve this, trying to upscale this model, we are going to face a lot of challenges that are not very traditional for the machine learning community in general. So in general, machine learning problems tend to have 3 main components. A model actually to train, data to fit, and GPUs to use. And in most cases, I'm talking about outside of the Earth system machine learning, we tend to have very large model, but very, very small data per batch. And for this type of problem, we tend to have a lot of solutions from model sharding to 0 stages, pipelining and checkpointing. There are a lot of ways of dealing with this type of problems. But for our case, the Earth system in general, we tend to have a small model, but very, very large data, which makes it extremely hard to fit into a single GPUs. And the only thing we have so far is manually parallelizing your model, which means your model is as good as your computational resources. So during this project, we're also exploring new ways of trying to train this model, and hopefully we can upscale it, such as progressive training or exploring learning the dynamics within the latent space. And successful implementation of this would actually really allow us to upscale these models both in high frequency and also in high resolution. And yeah, that's it for me. Thank you for your attention.
Thank you, Anass. That was a really nice presentation. Thanks a lot. Manita, you want to take over for the question? There is only one so far into
yes.
the chat.
Yes, so we already have one question. Thank you, Anass, first of all, for your nice presentation. So we already have a question in the chat, and it's from, actually we have 2. So, okay, the first question is, what method do you use in the eddy detection algorithm for the ocean? And the question is by Vitali Sharma.
For the eddy detection, it should be, it's pretty much a very simple one. We used a very known function that detects the closed contours in the SSH field, and it just try like see the convexity and try to take the outermost convex contour. It should be more or less the same one implemented in PyEddyTracker. It's pretty known library for eddy detection.
Okay, thank you. Dorothy, I will read out your question so in the recording it's there as well. Okay, the next question is by Dorothea. The question is, GLONET is trained on GLORIS 12 daily mean fields. To what extent do you expect the model would benefit from incorporating sub-daily variability, example tides and inertial oscillations, or rapid transient events? And how much improvement would you anticipate in forecast skill at short lead times?
Yes, GLONET actually, it is trained on daily means. And I would believe that including or retrain it, or at least fine-tune it on hourly data, be very beneficial. There are two classes. It's either going to work and work very well, because we could make the argument that it is very challenging for now for most of machine learning models to capture small-scale dynamics, because they tend to happen in frequency that is lower than 1 day. So including such data would help stabilizing the model and having them more robust for short-term forecast. But also there is another class which I could argue that including high frequency would trigger a lot of rollouts and therefore accumulating more error, and therefore it could degrade the quality of the forecast. It's something to actually try and see.
Thank you. Dorothea, do you have follow-up questions?
Yeah, I do. There is one from Shui, so probably you can go first with this one.
Okay, so do we have another question in the chat by Junju? Just to confirm that the ocean bench diagnostics are based on class 4, is that right?
There is a class 4, which basically you compare everything to observations, but also we have a track where you compare your models to the data used during the training. So you compare either to analysis or the reanalysis. So yeah, it includes also the class 4, but not only class 4.
Okay. This next question by Francois. Do you think that GLORIS 12 is the right target for climate application, knowing it is short and it has discontinuity due to the observation period?
This is really hard to answer, because for climate projection, it would be nice to train on an ensemble of models that are available for that. At the same time, there is an argument that these models are on very low resolution. We're talking about mostly 1 degree. Most of them don't have assimilations. So I would say I could give the argument that yes, that is the case. Training on GLORIS that already assimilate data would be nice if we could imagine a way to train it and also to be capable of extrapolating rather than just interpolating, which is very much known for the machine learning.
All right. There's another question by David Ferreira. What is the equivalent of the 2-week limit for divergence seen in the AI-based weather forecasting?
Sorry, I think it's pick the question.
What's the equivalent of the 2-week limit that you see in the AI-based weather forecasting?
Well,
maybe David can
GLONET and the most
speak up if the question is not clear.
If I understood, I think we actually stop at the scale of 10 days. That is more or less what is done in most of the operation centers. And it is actually true that we did run some of the models beyond 10 days. Well, some of them, yes, you can run in them because they are autoregressive. You could run them as much as you want. I could speak for GLONET that we developed ourselves. We did actually run it for a longer period, up to 3 months. And what we did actually see is most of There are two classes of variables. You have everything that is passive, let's say the temperature and the salinity, the tracers. They tend to degrade quite fast after 15 days. So you would start seeing a lot of artifacts building, especially around the coastline and the islands. But for the SSH and the ocean currents, it's quite surprising because they are pretty clean, even at the scale of 3 months. But one thing we did observe is a decay of energy. So you'll arrive to a very steady ocean after a couple of months. I don't know if that answers the question or not.
Yeah, I hope it answers David's question.
Yes, it does. Yeah. I was referring to the stability. But I think you answered the question. Yeah. Thank you.
Okay, great. I think there's another message in the chat by R. Keenan about Lyapunov timescale, but I don't have the full question. Do you want to ask it yourself?
Oh, I was trying to assist with David's question. I thought maybe he was talking about the Lyapunov timescale.
Okay, more questions? Can you just unmute yourself and open your camera and just ask? Meanwhile, there's a question in the chat by Giovanni Annunziata. Have you conducted training and inference experiments to assess the performance of your machine learning model using a different set of input features to those you have shown? And if so, what differences did you observe in terms of training, convergence, and inference performance?
I haven't trained, if I understood pretty well, I haven't trained the model on different data rather than glories. But what we actually have done is try to change a little bit the initial conditions and see if the model is going to respond positively or not on that. We have a PhD student who's working on that, and he did a lot of experiments, some realistic and some don't even make sense. Like you could just draw anything and see how it is going to evolve with time. And yeah, I would say the experiments were rather telling us that we are more learning the physics than just mapping between some images.
All right, thank you. We have still enough time for questions.
I can have another one, Manita.
Yeah, sure.
It's probably goes beyond the slides that you showed today, Anass, because I think it's if I remember correctly, you have into your paper describing GLONET, so you have the spatial distribution of the error for the different variable, and you compare the two models, GLONET with the other one. And if I remember correctly, the location of the error it's the same between the two. So it's the western
Yes.
boundary current, is the ACC, the Gulf Stream. Do you have an explanation for that? So
I would say just
yeah.
I think regimes that are pretty much hard to learn, and I could even give the argument that those regimes are quite fast, and probably daily data is not what we really need. We need actually probably high frequencies.
So it's just the dynamical
yes.
behavior of this area. Okay.
More questions? Otherwise, I have one. So you mentioned FESOP, right? That you also want to maybe connect the results to FESOM or try another model. Do you have also maybe plans to include other models, global models for?
It's really up to the community. So it is not me who's going to run FESOM model, but rather the group from AVI Institute.
Right.
So
yeah.
they were interested in entering the benchmark. So yeah, so I would be really happy to have like anyone who's willing to contribute to the benchmark.
Okay, cool. Thank you. I don't see more questions in the chat. I don't see any raised hands, but you can still just speak up if you have any more questions.
Just want to, sorry, I was writing. Just want to, could you, Anass, could you repeat it again? What's the major differences between GLONET, Xihe, and the other one? I couldn't remember, Wenhai.
Wenhai.
Yeah.
So GLONET, first, there is a difference in architectures and the way it is designed. So GLONET is it is not forced by the atmosphere. It is conditioned on T-1 T to give you T+1. Cheer is based on transformers, and it is a direct forecast, so it's not autoregressive model. It doesn't feed its own outputs, so it has like 10 models, each trained for a certain lead day. And when high, I believe it's based on, if I'm not mistaken, transformers, also a language model, but it is also forced, but not only by the wind 10 meters above the sea, but also by the other variables of the atmosphere. Those would be, and it is autoregressive. Those would be the main differences between the three models.
Okay.
And also there is the difference in times of resolution. GLONET, it's interpolated to 1/4 of the degree, so it learns the physics of 1/12, but it is going to give you an output on 1/4 of the degree grid, but the others are trained on a high resolution 1/12.
Thank you. We have one more question in the chat by Stefano Campanella. You mentioned using both batch and pipeline execution, parallelism, but only 32 GPUs. What was the batch size and how many GD iterations have been used?
So for training GLONET, as I said, we used 4 GPUs to perform what is known by model parallelism, which means you have one instance of your models, you spread it across 4 GPUs, so you have different parts living in different GPUs, and that's how you could fit the training. Otherwise, it didn't really fit within 1 or 2 GPUs. We really needed 4 for that. As for the rest, which is the number of nodes, it only allows you to train faster and generalize even better. Basically, you'll have 8 instances of the models, each living in different node and each training on different set of the data before sharing the gradient later.
Okay, more questions?
I have a curiosity. It's still Dorothea speaking. Mainly because GLONET comes from Mercator. They is in charge of the regional forecast systems for many regions. Do you think that using finer tuning will be possible to actually use GLONET for regional forecasting at higher resolution as done for the classical systems?
I wouldn't call it fine-tuning, but using the same architecture and train from scratch to different regions. We already have a plan to train something for the EBIT region. So we'll use the same architecture and try to see if it's going to fit for high resolution or not.
Okay, so not based on actually on the global application, but just do the same approach for the regional one. Okay, I see. Thanks.
I have a question about the trajectories that you mentioned. Yeah, when you were tracking them. So maybe I missed it, how long they were. And if you would have even longer trajectories, do you expect changes in the results from the AI model?
Oh, yes. Oh, the trajectories are 10 days.
10 days.
We'll initialize a 10-day trajectory every Tuesday. And yes, they are up to 10 days. And of course, if you increase them even more, we would see like larger day versions, of course.
Okay, thank you. Any more questions in the chat or somebody wants to speak up? Okay, if that's not the case, then we can thank Anass one more time for giving such a nice overview of GLONET and what Mercator is doing in this direction. This also brings us to a close for this webinar series, actually. So we had, this is the 3rd webinar that we just started. So let's say this is a winter webinar block, and this was the 3rd webinar. And we'll actually now take a break for 1 or 2 months, because next month is Ocean Sciences meeting. So most of us and most of you will probably be going there. So we will probably get back to you, around April with the next webinar series. Meanwhile, we'll contact speakers and hope to continue to see you in our continued webinar series also later. Don't forget us if we take a break for 2 months. Yeah, I think August will stop recording, and yes, you can watch the webinar on the YouTube channel anytime later. And